Hi everyone, and welcome to Eric's Electronics Workbench. So on the bench today I have this Agilent 6812B AC power source and analyzer. So I recently picked up this instrument, and the condition that you see it sitting on the bench right now is exactly the way that I received it. So I don't know if it functions. I've not attempted to power it up yet, and I haven't even removed the top cover, so I don't know what the condition is internally. So we'll find that out together as I go through the instrument, and we'll see what it takes to be able to put it into service on the workbench. Now you can see the hardware that's sitting on top of the instrument, the handles, the rack mount ears, and then the covers that go on the rear panel terminal boards. The seller that I purchased it from removed those pieces, and they were in a bag just off to the side. And that was a really good idea. Those pieces kind of stick out to the sides, and if the instrument took a hard hit in transportation, those pieces could easily be broken off. So it's nice that they went ahead and removed those. And to gain access inside the instrument, you'd have to remove those pieces anyway, so that's just one step that's out of the way for us. Now that being said, there is some unfortunate damage that I'm noticing on the instrument, and that's one reason I don't want to power it up just yet. So we'll take a closer look at what that damage actually is, and then we'll proceed to opening up the instrument and taking a look around inside and then making some repairs. I'm really looking forward to having this AC power source on the bench. I already have a Bellman Engineering KBT series AC power source, but it doesn't have nearly the comprehensive measurement capabilities and some of the other features that this Agilent model has. So this will be a really nice addition to the workbench, and I'm really looking forward to being able to use it. So let's get started on the repairs. So one of the first things that I noticed when looking at the front panel of the 6812B is that there is some damage along the right hand and left hand edges. So this is an adhesive back veneer that's applied to the plastic frame that creates the front panel. And you can see along this edge right here, that's buckled, kind of wrinkled a little bit. So it looks like this plastic edge was pressed inward at some point, and then that caused this to wrinkle or buckle out a little bit. So it'd be nice to be able to make this a little bit smoother again so that it doesn't have that cosmetic issue. It wouldn't have any effect on how the power supply operates, of course, but it would be nice to make that look a little bit better. Now a little more serious is this crack right here. This needs to be repaired so that that crack doesn't extend down any further. Right now it's just this corner right here has this little bit of a crack in the plastic right there, but the mounting screw for the front panel is right here and then right here, and then same on the other side, so there's 4 screws total. But the plastic around these screws is intact and has no issue, but we wouldn't want this crack to extend any further, and certainly this could get caught right here and break further, so that needs to be taken care of. Now, the good news is when the handles are installed on the side over here, this is really not visible back here, so even with a repair, if the crack is still something that you can see in the plastic, it won't be noticeable once that handle is installed. So over on the left-hand side of the front panel, you can see that this edge must have been pressed inward, and it's caused the veneer to wrinkle or buckle just a little bit right here. So I'll see if I can repair that. Just a cosmetic issue, but it would be nice to make that look a little bit better because you do see it all the time on the front panel. Now unfortunately right here, a piece of plastic has broken away. Now I have that little piece of plastic, and like a puzzle piece, it will fit back in here, so I'll use an epoxy type of glue and see if I can reattach that piece in there. But more concerning is this voltage control right here. So this is a rotary encoder. It's a continuous rotation, and you can see it's extremely loose when I move that around. Now compared to the frequency control over here, very slight wiggle is all, doesn't move very much, but this one is extremely loose. Now when you rotate these controls, they both have the same feel to them, so this control is not completely broken, to the point that the rotation internally is affected, but it's extremely loose, so I'm not sure exactly what has happened with that, but it's definitely going to require that that front panel be removed so that we can gain access to the back and see what's going on with this encoder. Now these rotary encoders work that when you rotate them slowly, the value increases slowly, and then as you rotate them faster, it increases the value proportionally quicker. This voltage and the frequency controls over here can also be entered directly by the keypad over here. So in worst case, if this control didn't work, you still would be able to change the voltage by entering it over on the keypad. But of course it would be nice to make this work, so I have to take a closer look at this. Now there's also an issue on the back panel, so we'll take a look at that next, and then I'll take the top cover off and we'll start to investigate inside and see what the condition is. Okay, taking a look at the back panel of the instrument, there are several things that I wanted to mention. So this terminal board right here is for the AC line input connection, and this terminal board over here is the output from this power source where you make the connection to the device that you want to power. In this corner over here is some auxiliary functions on this connector, and these two B and C connectors are for some triggering controls. Right here's an RS-232 connector for a computer interface, and right here's a GPIB connector for remote control of the instrument. Now you can see on this terminal board, two of the screws are missing, so I need to find replacement screws for that terminal board. Now, somewhat of a concern is that this terminal board has an upwards bend or twist to it, so it might be a little bit hard to see on camera, but it's bent or twisted upwards like this. So I need to make sure that there's no damage to the circuit board that this is attached to, and you can actually see that circuit board right underneath here. So I need to look for any cracked solders or any issues like that that are going on, and I'll do that once the top cover is removed and we have access to this circuit board or the assembly that this is attached to. Now sometimes these terminal boards can get bent like this one is because the instrument gets raised upwards like so, and the weight of the instrument presses on this as this is raised up. You know, this is the first thing that gets pressed or hit on the back side because it sticks out the furthest. So it's not uncommon to see these get bent a little bit, but again, you need to make sure that there's no damage to the circuit board or the solder connections. Now something else that I noticed is that the factory applied sticker right here says that this instrument is set for a 220 to 240 volt AC input power, but this instrument can be set for 120 volts, and that's actually what I want it to be set to for my purposes. So once the top cover is removed and we're looking around inside, we'll take a look at the voltage changeover connections, and I'll show you exactly what's involved with switching the voltage. Now, I don't know, maybe this instrument has already been set to 120 volts. There's no markings on the back that would indicate that, but it looks like it left the factory with the 220 to 240 volt range already set up. So we'll take a closer look at all that once we're inside the instrument. So the next thing that I'm going to do is remove this top cover, and to do so there's just 4 screws that need to be removed. There's 2 on this side and then 2 on the other side over there. So I'll remove those, I'll reposition the camera, and let's take a look inside the instrument. Alright, the top cover is removed from the 6812B, and there is a whole nother cover underneath that top cover, so it looks like there's some more disassembly to even get inside the instrument. Now, here's the top cover, and there's a lot of weight just in this, the heavy gauge sheet metal that they used. And you can see the sticker right here, it looks like 2011 inspection stamp right there, so probably about the year of manufacture. So with the top cover removed, this warning label becomes evident, and it's a good reminder of the dangers that are inside an instrument like this. So if you're following along, you're absolutely doing so at your own risk. There are very, very dangerous high voltages within this instrument. In fact, the DC rail-to-rail voltage in this instrument exceeds 1,000 volts. So it's not something that you want to mess around with in any way. You need to know the safety precautions that are necessary when working on an instrument like this. So again, you are doing so at your own risk. So be safe and take care. Alright, I have all but these 2 screws removed from this inside top cover, so I'll go ahead and remove these 2 screws, and then we'll get this top cover out of the way. So the top cover should just lift straight up and out. There it goes. Yep, there we go. Pretty heavy gauge of steel. The top cover has some weight to it. It looks like there's a date in this top right here, March of 2011, probably when it was manufactured. So wow, looking down in there, that's really busy. There's a lot going on inside this power source. Now one of the first things I'm noticing is extremely dirty in there. So all kinds of lint and dust, so it needs a really good thorough cleaning. Looks like the fan turns okay. It's not bound up, it seems to spin all right. But yeah, look at these cables. I mean, there's just lint and dust everywhere in here. It's all over the circuit board. Now, this has not been powered up in a long, long time. Everything's discharged, so there's no high voltage in here. There is an LED indicator right here, and then there's one on the side. It is right down here. And if those LED indicators are on, it means that there's high voltage present, so you definitely have to be very, very cautious. Again, this DC rail in this unit has 1,000 volts from the positive to the negative side, so extremely high voltage. You can see these very large electrolytic capacitors are everywhere in here. Those are going to hold a charge for a considerable amount of time after the unit is powered down. So the next thing that I'll do is to vacuum out the lint and dust that's inside this unit and then take it outside and use an air compressor and finish up with the cleaning, get everything cleaned up real nice inside. I'll go ahead and remove the front panel. I think there's probably going to be a lot of lint and dust inside of this just based on what it looks like in the rest of the device. And also this knob needs some attention, so once this is off, we'll take a closer look and see what's going on here and why this is so loose. So I'll remove this next, do some cleanup in here, and I'll be back when that's completed. All right, the cleaning and disassembly is underway. So you can see the fan is sitting up here. I've got it removed. The DC rail assembly, that circuit board that sits right here, I've removed that. It's sitting over here, so we were seeing it in this position, but when you flip it over, you can see the components on the other side. It was extremely dirty. All these heat sinks had lint and dust hanging all over them, so I've started cleaning on that. It needs a little bit more cleanup, but it's coming along nicely. And with that removed, gives access down to this lower area here, which is completely packed with lint and dust as well. And in fact, you can get an appreciation for how much lint and dust has accumulated if I zoom into this heat sink and grab a flashlight real quick here. You can see how those fins are, the lint and dust is just hanging on there, just really packed in there. Be some thermal issues, some overheating problems, I'm sure, with the airflow being restricted moving through those heat sinks. So that all needs to be cleaned up. So I'll continue with that. Zoom the camera back out a little bit here. So I'll check the fan. It seems to rotate okay. I'm not seeing any problems. The impellers need to be cleaned up, but it does seem to be otherwise in good order. But I'll power it up, make sure it's not noisy or having any issues before I reinstall it. And then the front panel, you can see that's removed. And grab that circuit board here. So that rotary encoder that was so loose, you can see that's this one right here. You can see how that rocks around. So it looks like we got lucky. There's no serious damage. It's just these metal tabs right here have been bent outward and then it's become loose. So you can see how it's rocking around there, but it's not actually broken. So I'll be able to squeeze those tabs down and make that tight again. You can see this encoder here, how that's pretty tight. I might tighten up those just a little bit more as well. But again, look at how there's lint and dust all over the shaft on that encoder right there. It's just hanging on every component and piece within this power source. So the vacuum fluorescent display looks like it's in good shape. Kind of scum and dust all over the glass. I'll get that cleaned up as well. Interesting, they have a RJ45 connectors for the interconnects on all the digital signals on many of the circuit boards. You can see these gray colored cables that are running around here, and also here on the front panel, it's RJ45 right there. So the whole front panel, the keypad, the display, everything, all that data passes through this RJ45 cable connector right here. And then the other wires are just these four over here that go to the power switch on the front panel. I'm sure that as it was, the keypad wouldn't have been working very well. If you look over here, there's this gold plating. Gold does tarnish. It's not immune from that. So you can see it looks like a scum all over it. It really needs to be cleaned up. I'm sure that keypad wouldn't have been very responsive to the condition that that's in. If you're not familiar with these keypads, you can see there's a little break in the trace between the two halves where the button goes, and then the button has a conductive rubber material, so when it presses down and that touches, it's making a connection between the two halves on the circuit board. And the microprocessor over here is scanning these rows and columns on the keyboard, and it detects the button presses and then knows what to do. So I'll continue with the cleanup and some of the repairs on that front panel, and I'll be back when I have some more updates. So I powered up the fan motor, and it's to be expected. It was starting to get a little bit noisy. The bearings are starting to get dry. That's typical on an instrument like this. It's seen quite a bit of use. So if you're not familiar with how you disassemble one of these motors, on this surface right here, there's a label, which is right here. So you just remove that label, and it gives you access to this bearing. And what you will find is that this shaft right here is poking through the end of that bearing, and there's a little tiny C-clip, very small, you don't want to lose that, but you remove that C-clip from the end of the shaft on this impeller assembly. That drops out, and with that out of the way, you can of course put some oil onto this bearing right here, drop there, and on this side you can put a drop of oil on that bearing, and the electronics and everything that's on the inside right there, brushless DC motor design. So what I typically do is put a drop of oil on one bearing and just let it sit for an hour or so one way, put a drop on this side, let it sit for an hour or so. So that motor will be good to go again. Should be nice and quiet. So I spent some time cleaning up the front panel where the keyboard goes. Let me grab the circuit board over here. So this is all taken care of now. You can see that's very clean over here. So the keys should respond correctly. Display is cleaned up, and of course this is repaired over here. I got these little tabs bent back down again, so it's nice and solid. It doesn't wiggle or move at all. And even this one was coming a little bit loose, so I got that tightened up again. So no issues with that. Be able to reinstall that. The circuit board has a rather unusual design. You see these tabs right here with this cutout, and then there's another one right here. So if you turn the circuit board over, a little bit of an unusual design. You can see this has this gold plating right here, and on the front panel, you can't see it right now, but this chassis is turned the other direction, but there's basically a metal piece. In fact, it is this piece right here. So what I'm pointing to, that metal, it's basically a tube. It's hollow in the center. This piece of metal touches this tab right here, and they're using basically the springy tension that the circuit board has. Very unusual. I'm not so sure that I'm keen on that idea, but you can see where that little kind of a mark is right there where it's been pressing against it. It basically makes a ground connection up into the circuitry here. So a little bit unusual. And then this tab over here, it just touches against a piece of plastic, and you lift this up to kind of release this circuit board, and the whole circuit board slides over and out. There are 2 screws on this board that you have to remove as well. So again, a little bit unusual design with this sort of a spring tab that's part of the circuit board, but that's what they designed. So, and on this circuit board over here for the AC power input, I have this terminal board repaired, so you can see now it sits at a 90-degree angle compared to the main circuit board instead of being tilted upwards. So there was no damage on the circuit board on the bottom down here, which was, of course, good news. So I was able to bend it back down, but in doing so, you're putting tension into these solder connections, and of course there could be a crack or something going on. So basically I just reflow the solder on those 3 terminal connections, which are these 3, you can see right there, the terminals that on the back side where this screw goes in right here, and then you can see that bar that kind of goes down to the circuit board. So when you're bending this back in place, any tension that's built up into these pieces of metal, by reflowing that solder, just releases that tension, make sure that there's no issues going on with that. So that is taken care of. I also found 2 replacement screws for the terminal board. So this is ready to reinstall. The reassembly is almost complete on the 6812B, so I'll be able to power it up soon, and we'll see if it functions. However, the next thing that I need to do is to reconfigure the AC input voltage range. It is currently set for the higher 220 to 240 volt range, and I want it to be set for 120 volts. So there's 3 areas of concern when you're changing the voltage range on this instrument. One is right here, this white jumper you can see on the circuit board. This just needs to be moved over to this other terminal connection right here. So the terminal that it's on right now says 200/220, and the other position is 100/120. So that's a simple thing to move over. Now, pardon the camera movement, but get this positioned over here. So in this corner over here, right above where my finger is right there, you can see there's a little chart down on the circuit board, and there's some voltage ranges printed on that chart. And there are 3 jumpers on a terminal block right down here, right on the circuit board, down in there. So you just follow this chart that's over here and the position of those jumpers and the voltage that you want. So that's, again, a simple thing to do, but you just reconfigure that. So I'll get that taken care of. And then, again, pardon the camera movement, but taking a look up here in this other corner, you can see over here there's a connection down on the circuit board, and then there's another connection that looks exactly the same. It's hidden, it's right back down in here. It's kind of hidden by this other terminal, but these two connectors have some voltage markings next to them. It's a little bit confusing because on the one connector it says 200 volts and the other connector says 240, so you don't see anything about 120 volts. But it's more of a range selection. So the 200 volt position is used if the input voltage is 100, 200, or 208 volts, and the 240 volt position is used for 120, 230, or 240 volts. So again, it's more of that range, high-low range, rather than just strictly voltage. Now, the connector that actually plugs into that is on this DC rail assembly right here. So you can see this large connector right here. So this whole assembly gets mounted across the front, and then that wire harness right here just reaches down and plugs into the appropriate connector. So I'll get all that taken care of, and then I will get the unit repositioned and we'll try and power it up. So I'll be back as soon as it's ready. So for the sake of completeness, let's take a quick look at the main component locations within the AC power source. I'll also get the block diagram of the instrument. We'll go over that real quick just to make sure we understand how the instrument actually functions internally. And then I'll get the top cover in place and we'll try and power it up for the first time. So in this back corner right here is the GPIB and RS-232 interface board right here. So the only connection to that board internally is this cable right here on this RJ45 connector. This large assembly right down in the bottom with these big electrolytic capacitors is the AC input assembly. There's a bridge rectifier right there under that heatsink. Some relays in this corner right here. Some resistors up in this corner right here, probably a soft start function. This choke right here is part of this assembly. This is the AC line choke right here, so it's in a type of inductor. The circuit board that's underneath this board, you saw previously there were some large heat sinks on some of the devices on that board. That's the bias assembly. This is also the bias transformer right here. So this is a 60 hertz transformer at this point. This is not a high frequency transformer. A lot of what happens in this AC power source is basically a switch mode design type power supply, so there's very high frequency switching going on to drive some of the transformers. But this transformer in this case is not, it's a traditional 60 hertz transformer. So this circuit board across the top is the DC rail assembly, obviously the cooling fan right here. And then this large heatsink assembly right here, the active devices are up in this front edge, but this is the AC FET assembly over here. The other heatsink on this side is the inverter assembly, and there's quite a few active devices you can see all across there, more FETs. Also some diodes, I believe, as well. Now you can see these heat sinks are electrically insulated from the chassis, so these plastic clips right here are holding these heat sinks away from the metal support brackets that are of course at ground potential, meaning that these are electrically floating and can be electrically live, and there actually is a notice right here that this surface may be electrically hot. So you'd never want to reach and touch these when this is actually powered up because you could get a shock on those heat sinks. Now over here, these large electrolytic capacitors are part of a circuit board down on the bottom, and that circuit board is the output filter and relay assembly. This back corner where these two gray cables with the RJ45 connectors go, that's the trigger assembly, just some auxiliary functions on that. This circuit board right here is the digital signal processor, or DSP, and on the other side this is the main control card right here. And we already saw inside the front panel, which is just slightly out of view up here. And there's a processor within that front panel, and obviously the display and the keypad. So let me grab the block diagram and we'll just run through real quick and see exactly how this instrument functions. Here's the block diagram for the 6812B AC power source. So starting in the upper left-hand corner right here, we can see the main AC input, and that AC line voltage is applied to the AC input assembly. So there's two things that happen here. The AC line is applied down here to the bias assembly. This is just a 60 hertz AC line voltage that's coming down to a 60 hertz transformer on the bias assembly. And this is creating numerous DC voltages within the instrument just to power all of the support circuitry. See the line switch right here is affecting the bias assembly as well. Now, on this AC input assembly, there's rectification and filtering to create a high voltage DC. So the rectification is probably set up as a voltage doubler on the 120 volt input, and on the 240 volt input, it's likely set up as just a straight bridge rectifier. But nonetheless, the high voltage DC output comes over to the FET assembly, and this AC FET assembly is switching that DC voltage at a very, very high frequency. So that high frequency AC is driving this power transformer, and this power transformer can be much, much smaller than it would be if it was a 60 hertz type transformer. The output of this transformer is of course a high frequency AC signal, and it's coming into the DC rail assembly. And you can see there's a rail choke, some filtering going on there. And the DC rail assembly creates a very high voltage DC, which comes over here to the output, filter, and relay assembly. But that high voltage DC is actually returned back over here to the inverter assembly. This inverter assembly is really key because it creates the various voltages and frequencies that this AC power source is capable of. So you can see the output can be 0 to 300 volts AC, and it can vary from 45 hertz to 1 kilohertz. So all of that voltage and frequency control is happening because of this inverter assembly. Now, the output can actually extend below 45 hertz, and it can go all the way down to DC, and at DC the output can be fixed at up to a plus or minus 425 volts DC. So basically you can have an AC output with a DC offset, or you can take the AC away and just have a steady DC output voltage. And you can vary the DC again from 0 up to 425 volts DC. So very flexible output, capable of quite a few different configurations. This does not have to be a sine wave. This can be an output, it can be a square wave, it can be a clipped sine wave, it can be an arbitrary type signal, so very, very flexible in what it's able to develop. Then you can see down here various support circuitry. We have a digital signal processor, the main control card assembly, just tying everything together, the RS-232 and GPIB interface that we saw, the trigger assembly, the control signals going around on those gray cables with those RJ45 connectors on them, coming over here to the bias assembly and passing through to the front panel assembly. Okay, let's see if the 6812B AC power source will power up and function correctly. Now, I've reinstalled this inside top cover on the instrument just as a safety measure. There are no internal adjustments on this instrument, so if it does need any type of an adjustment, it would all be done from the calibration on the front panel over here. So again, as a safety measure, this has been reinstalled. Also, this will help the cooling because the fan blows the air down the heat sinks and exhausts out the back, but with this top cover on it, make sure the air is drawn in on the sides and then the air passes over the components correctly internally. So you can see my digital multimeter is connected to the instrument's rear panel output terminals. So the digital multimeter is showing frequency or hertz on the top line of the display, and the volts AC measurement is on the bottom line of the display. All right, let me turn on the bench power. Okay, AC voltage is turned on, and I'll reach over here and see what happens. All right, that looks good. Display self-test, some startup displays, says wait. And we do have a display, so excellent. That's looking really good. So now the output is turned off right now. It says DIS, that's disconnected, so the indication right there on the display. So let me reach around over here and I will put in a voltage. Let's try voltage. Let's make this say 10 volts. And then I'll turn the output on. How about that? So we do have 10 volts over here. It says 10.03, so very close. And on the digital multimeter, it says 10.004, 10.007, so very, very close. That's no problem at all. So it looks like the voltage is right where it should be. And the frequency is set to 60 hertz. And that's what it's showing over on the display on the digital multimeter, 59.998. So right at 60 hertz, that's looking really good. So if I come over here and I try this voltage control, yep, that works. So as I rotate that, that's increasing the voltage. Now it's a little over 12, there's 13 volts, 13.03. Digital multimeter is agreeing with that, no problem there. Again, this was that rotary control that was so loose, so it is working okay. I change the frequency, yep, the frequency goes up. Frequency can shift down, no problem there. Let's try frequency. Let's make this something like, let's say, 400 hertz. So 400 hertz, 400.00. And the display over there, 399.98. No issues with that. Let's try something really low. Let's try, like, say, 30 hertz. No problem there. 29, 30 hertz on the display, no issues. Let's increase the voltage. Let's try something like, say, 240 volts. Okay, very nice. So this is 239.8 and 239.78 on the display, on the digital multimeter. So really looking good at this point. No issues with how it's performing. Now this can take some measurements, total harmonic distortion. It can do different types of waveforms. So let's take a look at some of those features. And what I will do is connect an oscilloscope to the output so we can take a look at the output waveform. And then I'll also connect a load to the AC power source so we can see how it performs with the load connected. So I'll reposition things and I'll be back in just a minute. Okay, I now have the 6812B connected to a 100-watt incandescent lamp. So that's acting like a load on the power source. You can see the power source is set to 120 volts, and over here we have 119.9897, so no problems there. You can see on the Fluke Scopemeter over here, it's indicating 120 volts. So the sine wave on the output is the red trace. That looks very, very good. No distortion, looks really spot on, no issues with that. And then the blue trace over here is the current waveform. So if you look over there, that's a current clamp that's sitting back there, and you can see that little red wire that's passing through it right above my finger back there. So that clamp is just around that red wire, and it's measuring the current going over to the incandescent bulb. So we can see that the current is in phase with the voltage, which makes sense on a resistive load. So no issues there. And then this is indicating 100 watts. So I have this Scopemeter calculating the wattage, and it can do that because it knows what the voltage is and it knows the current, so it just makes a wattage calculation. And over here we can see this is also indicating 100 watts. So everything matches up, looks spot on, no issues whatsoever. Let's take a look at the constant current mode and make sure that that works all right. So you can see it says CV in the corner right here. So that's constant voltage mode, meaning it's holding the voltage constant. It's entered at 120 volts, we're right at that. And the current value will vary depending on the connected load. So typical of most power supplies where you have a regulated output voltage and then the current varies as you change the load. So we can see over on the Fluke Scopemeter, it's indicating 120 volts and then 0.83 amps. And right here we do have 0.836 amps, so that's an agreement. So let me change the current now. So if I go over here to the output, go shift and current, so we can see the current level is actually set to 6 amps, and we're well under that, of course, so only at 0.83 right now. So I'll make this something smaller, we'll go 0.3, so 1/3 of an amp roughly. Hit enter. So now it's going to detect that that current value is above 0.3 amps. We can see it's already gone into the constant current mode, so that looks good. And it should begin to program down to match that 0.3 amp value. Yep, there it goes. You can see it's dropping. I don't know if you can tell in the camera or not, but that incandescent bulb, it's off to the side over that way. It's getting dimmer. If you watch the Fluke Scopemeter, you can see the waveform is falling down smaller as the voltage is dropping. About 60 volts now. About 1/2 an amp right now, so that's still above that entered value of 1/3 of an amp. On the Fluke Scopemeter, it just auto ranges. That's why that waveform jumped up. The voltage did not jump. Down about 0.4 amps now. It's still falling over here. So what it's going to attempt to do is hold the current constant at 0.3 amps, and then the voltage would be allowed to vary, and it will do what it needs to hold the current constant, thus the constant current mode. So we're almost there. It says 0.33, getting very close, so it should stabilize at about 1/3 of an amp. 0.32, got it only about 16 volts now, 15 volts. The bulb really isn't glowing at all at this point. And we're very close right now, so we're at 0.3 amps right here, so it looks good. It's hit that point. It really shouldn't fall much below that. Looks like it is stabilizing, 0.29. So we're down clear to 12 volts now from 120. But that's what it takes with a 100-watt incandescent lamp to get a 0.3 amps through it, or 1/3 of an amp roughly. You only need about 11 to 12 volts. So it's holding pretty close to 0.3. Just a little bit under that, but not too much. Go to 1/2 an amp. It should allow that to rise up now. Goes the other direction. It should stabilize at about 1/2 an amp. You can see the voltage is now programming back up again. Again, it will set the voltage to whatever value it needs to get the current at the value that's been entered. So we should see that come up to about 1/2 an amp. It's a very useful feature, nice to have that constant current mode in an AC power source. So now we're up to about a little over 34 volts. Looks like it's about to stabilize there, 0.47, so just slightly under that 1/2 amp. So it seems like the constant current setting is just a little under the entered value. That might be a calibration issue, but it's not too far off. So it looks like that function is working reasonably well. So the 6812B has the ability to distort the output waveform. So you can see right now there's a nice sinusoidal waveform on the Scopemeter. That's the red trace, no distortion, looks very nice. But if we come over here and we go to the shape, and I go down to clipped sine, so it says C and then sine. So now you can see the output waveform has the sine wave clipped off on the top and the bottom of the peaks. And the output I have set to 50 volts. It was at 120 for some of the other examples that I was doing. It's set to just 50 volts now. But very distorted looking waveform. You'd have to use that with caution because certain types of loads could be damaged with a very distorted waveform like that. So it has its place for testing, but does need to be used with caution. Go to shape, down to square wave, and we can see a very squared off looking wave there. The blue trace is the current waveform, and you can see it's also very squared off, of course. Alright, here's checking the power factor reading, again with the incandescent bulb. A resistive load should be a 100% or a power factor of 1, and we do have that. So you can see over here it's indicating 1 point and then all zeros, so 100% power factor, and over here also it's 0.99, so right at 1. So everything's in agreement there, looks very good. You can scroll through some of the other readings that are on here. You can see volt amps reactive, or reactive volt amperes, 1, makes sense. See the VA rating 100.4, 100.5. So the VA rating volt amperes would be the same as the wattage on a resistive load. Did I go past that? Nope, there it goes. Okay. The amps peak right there, non-repetitive, peak repetitive, crest factor, the volts and wattage, and amps and frequency, volts and amperage, volts and frequency, and back to the power factor again. So all the readings are in agreement with the Fluke Scopemeter. I've gone through everything and everything keeps matching up. So it looks like the calibration on this instrument is really close. I'm not seeing any big discrepancies, so that's nice to see. So now let me connect something other than an incandescent bulb, and we'll take a look at how the waveform looks on a switch mode power supply as the load on this power source. Alright, for the last example, I have a switch mode power supply connected to the power source. So switch mode power supplies are notorious for causing poor power factors and other issues on the AC line. So let's take a look at this particular model. It's made by Lambda. It's a fairly large switch mode power supply. Outputs 24 volts at over 20 amps capability. I won't be pushing it to that full output for this test because my test leads won't handle that kind of current. But you can see right now there's no load on that switch mode power supply, but it is turned on, and in fact there's 3 fans running in here right now between that external power supply, the power source, and my dyno load, so pardon the noise that you might be hearing in the background. But you can see on the Scopemeter right now that current waveform is very different from what we saw on the incandescent lamp. So the red trace is the voltage waveform, and it looks the same, nice sinusoidal waveform. But you can see the blue trace is very, well, almost distorted for one thing. It has a very sharp spikes or peaks to the current waveform, and you can see those occur right at the point, at the high point on the sine wave for the voltage waveform. But it's not a very nice continuous current waveform like we saw with that incandescent lamp. Now you can see over here the power factor reading is 0.37. It's a very low power factor, and that's in agreement with that Scopemeter. You can see the power factor reading right up there, 0.37. So if I come up here, and I have to reach around the camera a little bit here, but I'm going to increase the load on the power supply. So it's outputting just 1 amp right now, and you can see how those peaks are much larger now on the current waveform. The power factor has improved a little bit, 0.4, but still not that good. Now we can come over here and look at the distortion. If we go to shift here, harmonic, so we can see it says 0.2% total harmonic distortion on the voltage waveform, and we do have a nice sinusoidal waveform over there, so that makes sense. Look at that current waveform. The total harmonic distortion is 91.2, so a lot of distortion on the current waveform. So it looks like this Agilent 6812B AC power source is ready to put into service on the workbench. It's functioning very well at this point. I'm really happy how it turned out. Now there's a calibration procedure that I'm going to go through and just double check a few things. I want to make sure it's spot on and can be trusted for the various readings and capabilities that it has. But overall, I think it turned out very well. I'm very happy with how the front panel turned out as well. You can see these corners, it cleaned up really well, so it looks very presentable. So if you enjoyed this video, don't forget to give it a thumbs up. And if you're enjoying the videos on this channel, please remember to subscribe. There'll be many more videos like this in the near future. And if you have any comments or questions about this project, feel free to leave those in the comment section. I definitely try to read all the comments, and if I can answer a comment or a question, I certainly will. So until next time, take care, and thanks for watching, and bye for now.